This is our device. The device transmits a wireless signal which reflects off a person's body and comes back. It captures
Okay, very quiet today, very, very quiet. How is everyone, how is your semester going? Good? All right, I hope, yeah, imagine if we do a worksheet today. Okay, let's get the lecture started. So today, I'm gonna give you a special topic around like health sensing in embedded system, especially from like a HCI perspective. Basically, those devices and systems that's built in a portable and more accessible ways for daily patients or users, rather than those big chunky devices or equipment that's built mainly for medical professionals. Before we go into the topics today, let's get some announcement out. We have the exam 2 grades released. I have a feeling that everyone showed up today, did pretty good in the exam. We have mean and median all around like 74 points. We will be basically capped the score at 100, so it's essentially out of 100. Whatever scores you got, that's how we're gonna count it. And we have the regrade opening until the next Thursday. It's Thursday night. So any questions you think you should get more credits, some partial credits, etc., please feel free to submit a regrade request in the scope. Any questions regarding the exam 2? Okay, sounds good. And another thing is the team presentation. So the topics and the data are assigned in the, you can find them on the class website. Make sure you take a look and then, mark the date. And then starting will be the next Tuesday. So about, 5 days from now. We will release the sign-up sheet after this class, so that you don't just find like a 30-minute slot that either me or James or Matt is available, and then spend 30 minutes with us, and then goes through your presentation slides and your structures, etc., as well as any questions you might have. So please do make sure you sign this up for at least 1 day before your presentation, so you have enough time to do some revision if needed. And if you do want to swap your slot, talk with other groups first to getting the other group on board. So as long as they're okay with you swapping the group, we are generally pretty open for those if you have schedule conflicts. The current topics were ranked as how relevant to the majority of the class. So if possible, try to stick to the current schedule, so that the more relevant topics will get to majority of the class for like earlier in the day rather than later. Any questions regarding the student or like the team presentation? Okay, so each lecture we're gonna have like 4 teams, so it should be like pretty chilled for most of the time. Make sure you do participate in those lectures, because we do take attendance for that via like the Google form. Basically, you will grade each other's, or like you will review each other's performance and the content they covered, and those will count towards your participation score. We do allow you to skip 2 of them, but that's if you want to get 4 participation points, at least show up 5 out of those student presentation lectures. And please do make sure to show up at least on your own presentation, so that you also have like a pretty decent grade together with the rest of your group. If you have any other accommodation requirements, feel free to send us an email and we will see what we can do for you. I know that we have one members currently abroad, so we could have them record their sessions, but generally speaking, you should expect it to be in person, standing here and present to the entire class. All right, so for today's topic, we're going to give you like a overview around like the topic health sensing or health sensing devices in the embedded system from a HCI perspective. So before we jump in, what is HCI perspective, or what is HCI? It's human-computer interaction, basically a multidisciplinary research field that focuses on the design, usability, and interaction techniques between the human and general speaking computer devices. Usually it combines the professional knowledge from EECS or sometimes cognitive psychology and other engineering fields to improve how people use the digital systems as well as like available technologies nowadays. So traditionally speaking, as you probably would thought about it, traditionally speaking, the perspective from this or like from the usability point of view for the health sensing devices usually goes to the user interface design or like the safety or accessibility of the interactive medical devices. For example, if we look at this devices, it's going to sound a little bit trivial, but oftentimes these displays and how they lay out really matters in order for the clinicians and doctors to have like accurate readings. But just if you look from the angle, you can't really tell what is that. Is it an H or is it an 8 or something, other numbers? And it turns out to be actually 9. So this is like in the earlier days or like more traditional perspectives of the HCI on the health sensing or medical devices perspective. Basically, make sure all those displayed and UI interfaces that make sense to mostly the professional medical doctors and clinicians. Also, different units sometimes also quite matters. Just make sure you have all of them laid out and tested in a way that none or like a very minimum amount of errors that could happen during those critical tasks. So different from that, what I would call like what more technical HCI perspectives or more relative to this class, basically from a more embedded system perspective, is the around this health sensing is usually surrounding the novel sensing technologies that improves the accessibility, basically getting more people to be able to access to those health sensing techniques, as well as portability, which means you can carry them around outside of the clinic. You can enable more like sensing environments outside of the clinic settings, as well as lower cost, so that all of these devices can be more like largely distributed around to like underdeveloped areas or areas that doesn't have as quick access to the medical resources. So what are we actually measuring in most of these cases? Probably you'll guess biomedical signals, right? Or some sort of physiology signals from the human body that coordinates with how well your body is performing. And that is correct. So they are a bunch of like biomedical signals that we could collect, just like in the clinic. For example, the ECGs, the electrocardiogram, the EEG, basically in a way your brain wave, EMG, which is the signal that's generates through the neural system to your muscle tissues that triggers the muscle engagement. ERG and EOG, basically. The EOG is the movement around your eyes, the signal caused by the movement around your eyes. And the ERG is the signal that's generated by the retina movement inside of your eye as well. So a bunch of these signals that's already currently on your body that's totally within our range of measurement. But we actually can do more than that. So apart from the existing signals that's currently on you, or we can call them, I think, passive measurements because they're there, you just basically putting your device or putting electrodes on them to amplify the signal and capture them. We can also do something more active or sometimes even quantitative. So more active meaning we're able to choose like specific signals that inject into your body and then measure whatever your body reacts to that signal. For example, we have sometimes the bioimpedance signals, injecting like an AC signal and then measure how well or how does it travel through your tissues, which corresponds to certain issues or certain conditions of your tissue. As well as biooptical, a bunch of different ways to kind of look into your body, either through say like CTs or like ultrasounds, all those sensing technologies. They essentially are all injecting or inducing some of these additional signals into your body and then see what the reflection looks like, essentially. And apart from that, there's also like body behaviors. So, your body, how you behave every day have a lot of coordination with how healthy you are or how healthy you will be in the long run. So those are also like a pretty active fields, basically the ways to record your behaviors. And these also including like diary, what you eat. There's an old saying that you are what you eat, right? How do you measure all those, record them, and then do analysis on top of that. So now that we know what kind of signals or which type of sensing method we're looking for, let's look at how the health sensing in embedded system gets where we are today, which is small portable devices, and also why is that? Let me give you a brief architecture of a typical health sensing systems, which should look very familiar to you now that you have taken 2/3 of the class. So basically, it's the same as most of the embedded systems that interact with human. Basically, you have human somewhere there, and then there's some method that take the signal from you. It could be taking a look at the signal that you inject into it, or it could be the signal that's originally be there. And then that goes through some type of like amplifier and filtering systems to narrow down which type, exactly that type of signal you're looking for. And then goes to usually ADCs, because obvious reasons, we have to convert those signals from analog to digital in order for your devices to better analyze them. And then we will do a bunch of like signal processing, and then we, in the end, if we do want to output something, that might have some output or display systems, or if you want to do some like real-time intervention, you could have another DAC system linked back there so that it generates interventing signals and then inject back to your body. So basic health systems, and this holds true throughout the entire time when we have computers, basically. So before that, these are one of the pretty old EEG machines. Not sure if you guys do have done EEG measurement in clinic nowadays. Usually they now have like one of those handheld devices that can measure you pretty decently. Unless, of course, you stay in hospital for like some emergencies, then they actually wire you up with some fancier device that does continuous and longitudinal monitor for days and nights. But this was back in the day. Basically, that's how a smallest, almost any like an EEG machine would look like, and this whole machine is like purely analog. So at that stage, there's not much thing we can do from like embedded system perspective, meaning that there's just no technology available that we are able to make these devices to like a more portable form factor that's able to be used outside of the clinic. At the time, all those devices usually, just as you remembered, or your parents remembered back in the day when the computer was like half size of the room, and then with the time developed, that become like gradually smaller, and then new field coming around, which is embedded system and then embedded system in-house sensing. The first wave actually comes in the 1980s, which is, like we said, it's the development of the large components to a smaller digital components, namely the ADC, actually. That's the time we start to be able to make those small pieces of ADC chips that can reliably sample and convert those analog real-world signal into a digital form. So this is one of the early stage commercial, actually. So that was kind of claim that it's able to read your mind and then use your mind to control whatever devices you have. And it uses I think one of the signals we mentioned before, the electromyo, or like the male neural signals is essentially the EMG signals that's for the control of your room. So I'll give you like a 30-second brainstorm here. is there anything like not adding up here? Like, is this commercial actually does what it claimed to be? Although this is like a first step, not only into, I guess, health sensing, but in general, portable devices, not an embedded system. But yeah, take a 30-second, talk to your neighbors, and see if you can spot any flawless ground here. Any thoughts? Anyone who have any challenging thoughts on this commercial back in the 80s? Any thoughts here? Yes.
If they're just measuring voltage on your forehead, if you use your muscles in your forehead, wouldn't it just think you're doing stuff like you're thinking?
Yes, exactly. So basically, as you spotted, it's a male neuron signal, right? Essentially, muscle movement underneath. So I guess when people think really hard, they do tend to, make some muscle movement on your front head. But is that really what your mind is, or is it just doing some performing? Nobody knows. So as we briefly talked before, if you do want to measure the brain activities to a certain extent, you could, or like the more accurate or like more accurate signal to look at would be essentially EEG. Or if you wanted to go invasive, then Neuralink is the way to go, I guess. But if you don't want to open the hole on your head, EEG still works fairly well for those simple tasks around just controlling stuff around you. But not sure if you guys actually worked with it. It's actually very noisy. As you know your mind, they're all pretty noisy, which reflects on your signal as well. But anyway, so like we mentioned, basically, this is where the analog to digital converter and the operating amplifiers, those analog pieces became like super cheap and be able to like massively accessible to the industry and to researchers. And that's where the first wave of this health sensing in embedded system start to coming along. And a little bit later, we also have the algorithm efficiency implemented on chip processors happening. All those previously it's more just faster and faster chips, and then later on we have like a huge wave on the ML. So the cloud was added to your equation. You're now able to dump those big chunk computation burden to the cloud, so you can retain the small form factors of your device. And then later on, of course, more towards nowadays, there is a trend of like tiny ML, basically have like very, very specific but small sized ML models to deploy on chip. So these generally the improvement on the signal processing and contributes largely to the wave or the trend of this health sensing with portable embedded systems. And this is where the Ubicom or like a CI researchers jump in. So traditionally, before these devices, traditionally health sensing or health monitoring usually requires you to visit doctor every once a year if you don't have any preconditions. If you have some conditions, maybe check with them every couple months. And then it basically results in obviously very rich data, but it's very very low frequency on the time frequency on the time domain. So basically, you have very few points on like the temporal axis, and it's usually like reactive, not preventive. Meaning, if like I said, if only you have some certain conditions, or if you doesn't feel well, that's when you're gonna go check it out, as opposed to if we have something to monitoring like a much higher frequency in terms of the time that can give you some preventions ahead of time, which is what we actually are trying to do here. With the novel health sensing devices, portable or new sensing technologies that previously does not be used or does not exist for these type of biomedical signal sensing tasks, jumping, and then to enable the vision of trying to measure you anywhere and anytime if needed, and provides like more data points, and then generates those preventive warnings ahead before you get injured, for example, as well as make the device much more accessible to different people even without resources of the medical resources like people, I guess, sitting in this room. And then, so next, I will talk about some of these efforts in each of the, in this trend by basically how close of these devices are to your body. Generally speaking, there is like non-contact, and then somewhere you kind of interact with it daily, and then something you wear on you, and then something stick on you, as well as something go inside of you. We're not necessarily going to go from this direction because some of them have like much more work generated based on that platform than others. So I will more go through them from like a more widely used or widely researched platform, and then down to a little bit like less explored, but like still very active fields. But keep that in mind. This is basically like a general, what are the, but generally speaking, how the distance of the devices and to your body, and which type of signal it's able to measure based on this closeness to your body. So first, we were gonna go into, of course, the smartphone-based, because as of today, or as of last year, about like 91% of people in US owns a smartphone, compared to, I think, the next biggest one, probably like smartwatch. It's only 26% that owns like a smartwatch in the United States. So let me go through some of the very interesting devices or like types of work that happen within the medical. So first is the anemia. Not sure if you guys are familiar with this type of disease. Basically, it's strongly associated with child malnutrition, and it contains, it's essentially a measurement, or it's essentially you don't have enough amount of the hemoglobin inside of the blood, which is the cells that's in your blood that carry around oxygens. This is pretty common in like the developing countries, or like in rural areas, or like areas with like higher altitude. And previously, it requires to draw blood to do like a more or less accurate measurement of how much hemoglobin in you. But with the development of the smartphone platform with all the computational powers it has, as well as those very nice embedded system or peripherals, those chips, those devices on board, we're able to actually now measure these hemoglobin level based on the phone on your camera. Sorry, the camera on your phone. That basically will give you like a rough, pretty decent accurate, pretty decent estimation of how many hemoglobin level you have in your blood. The science behind it is essentially the phone will shine different wavelengths of the light to your fingertip, and then based on that, because of the different parts of your blood, mainly like the plasma and hemoglobin, that have different absorption rate of the different wavelengths of the light, the camera essentially measure the reflected light, after the absorption, and then analysis on top of that, and give you an estimation of essentially how red your blood is on your fingertip. Let me give you a quick
It's conceivable
demonstration
that we
here.
can incorporate all the lights into a phone case.
Can you hear it? Okay.
We also found that infrared spectrum of an incandescent light was a good alternative to a custom case. By measuring the absorption of the blood under different wavelengths, a machine learning algorithm based on data from a clinical study can determine the hemoglobin in the blood, all without ever having to draw blood. In the same clinical study, we compared our results to an FDA-approved non-invasive hemoglobin measurement system. and found that our system performance was comparable. The biggest difference is we can use a smartphone's camera to do all of this.
Yeah, if you look closely on that, there is an additional piece of hardware attached to this the mobile phone with like a surrounding LED lights. That's the additional light source that give you the control over different wavelengths of lights that shining through your fingertip. You can probably get like a sense of how a lot of these devices are developed. They basically, if you think about them, you basically look at what's the current way of doing it inside of the medical world and see what are the sensors we have on our hand that's more accessible to everyone that can essentially perform the similar tasks to this type of sensor. For example, these FDA-approved sensors, they basically have like a little optical sensor inside that looks at your finger. So, and if you think about it, on your phone, the camera is essentially like a much more powerful optical sensors that traces your light. So with the correct signal processing on the camera data, you are essentially able to get very similar data. And then based on that, you do the analysis and then give you a related, like quite accurate result. This project actually deployed in Peru back in summer of 2017. I was also part of this project. It was pretty cool. Next thing is blood pressure. So blood pressure, you guys are still too young to figure to get a hand on this, but you know, once you hit, I don't know, 40, 50, the percentage of people who suffer from high blood pressure is going to be much higher than, well, I guess that's true for all the disease, but especially for high blood pressure. And there are various ways to measure the blood pressure. The most, I guess, the most common ways you guys will probably see is some like type of like cuff wearing devices or on the upper arm that basically apply pressure on it and then measures the two, like a higher point and the lower point, two pressure points, and then decide your blood pressure essentially. There are actually other ways to measure this. It turns out the blood pressure have a very strong coordination with the PTT or pulse transmit time. It's essentially the amount of time that the blood travels from your body, like from the heart to the end of your limb. And then if you record this for like a continuous amount of time, that actually have a very decent coordination with your blood pressure. So acknowledging that, we built a devices basically trying to measure these two signals. Basically, when the blood comes from your heart, and then when does it reach your end, and the end of your limb. So the two signals, well, I guess two signals we measured primarily to decide this PTT, pulse transmit time, is first it's called sesamon cardiography, which is measured on the IMU sensors on your phone. Basically, look at the shaking of your heart. It's actually called BCG, or like, I guess you can also just think of them as ECG of that wave. That's what the IMU is measuring. And the second is through PPG sensors, which measures when the pulse reaches the tip of your finger. The PPG sensor is like widely used in, I think, probably almost all the smart watches nowadays, or Fitbit has one in it to just measure your heartbeat, etc. So, basically what happened is you have the phone here pressed to your chest, and then when the heart started pumping, the first peak, or like one of the peaks that indicating that's when the blood start to coming out of your heart, and then you also have the other hand, the fingertip on the phone, which measures similar things as we saw in last video. Basically measured what time the finger pulse, like the pulse reaches your finger, and then using that, we're able to interpolate your blood pressure on this. Cool. A few other things, including also jaundice. Not sure if you guys are familiar with this, but basically it's essentially like a more yellow or greenish appearance of skin and eyes. This is due to usually the bilirubin levels, and that if you don't treat them in time, that usually leads to like liver failures, etc. If it's like babies, it's going to be having some like brain damage, etc. But if you're able to just diagnose it in time, it's actually quite a well-studied treatment. Just over like a week or so, you shine the baby under specific wavelengths, and then you have like a more color-calibrated baby after that. So, which is pretty nice. But anyway, nowadays, usually the almost only way that's to test these is still like doing drawing out your blood. But if you just think about it, it's pretty hard for drawing blood from your baby because their vessels are so tiny and then they move around a lot. So not optimized. So what can we do about that? Again, the magical camera comes in. Let me give a little bit more background. Because of the whole CMOS sensor that's on the phone, a lot of these companies are driving super hard on getting extra pixels and make the camera to be larger and multiple cameras and all those efforts. They leads to obviously better selfies and Instagram posts, but it also happens to leads to a lot of other good stuff like health monitoring and stuff. So basically, what we did is we have a color calibration card put onto the baby, and then we just take pictures at various different heights under various different light levels, like a controlled light source. And then we do the color analysis, and then see how how yellow or greenish this baby is on the skin, and then decide and interpolate what's the the bilirubin level inside of their blood. So this work is also done at University of Washington. They actually collect the data from more than 300 newborn babies at the Seattle Children's Hospital, which is quite a lot of work. I can't imagine the amount of IRBs and paperwork they have to go through in order to perform these for newborn babies. And we also have, they also have the methods for like more adult measurement. So for adults, it's less likely. If you get it super severe, it's also show on the skins. But more accurate ways to do that is actually to look at your eye and see how the surrounding of your eyeball, the color of that, and use that to determine your bilirubin level. So similar to that, instead of putting a card on you, you just wear like a very nicely designed glass color calibrating card glass, and then you use that to take pictures just like before at various different light source and distance to get like a good like a good measurement of these of the color. So I was actually working on developing and commercializing this project back in my time at UW. They did like a startup thing out of this, and fun fact, you can't really purchase 200 phones at once in the United States. They will think you as like a drug dealer or something. Next time you want to go to Apple Store and try purchase 20 iPhones, don't do that. They put you on a list. So it was pretty cool to work on this project. The company later got acquired by Google, so everything worked out. Something along this line, we have the asthma monitoring or like lung function monitoring. Basically, you guys probably done something like this, right? Basically, you blow into this machine, and then based on how much air you're able to produce, as well as what's the pressure, they calculate out a number of, and then get like a corresponding evaluation of how well your lung functions. It's usually basically just determined by the flow and the exhale volume. So again, since we're still under the smartphone platform, so because we have those pretty accurate microphone sensors built inside of the device, we're able to evaluate this type of motion. Of course, we can't really measure how much air that goes out, but we're able to record the audio sound and then use this like reverberation sound surrounding like the user's head, and use those sounds to give you like a approximate of how well your lung function is. Let me give you a quick, be aware. So yeah, that's basically the amount of air that comes out being like I guess regressed from the sound data, and then you will probably think that okay. The good thing is you are now able to do this anytime, anywhere. But the bad thing is you probably don't want to do it anywhere, or in front of your family, or in front of your friends, or during a party or anything. So it's kind of like socially awkward. It's kind of like vomiting on your phone, so to speak. So later on, the team actually have like an updated version, so that you blow into a spiral whistle instead of directly into your phone, which does not help much, but it looks more professional. Another thing is we can detect with is the like the traumatized, like the brain injury, or like the early stage brain collisions inside of some like combat sports or American football apparently. So normally those if you say like if you watch those NFL or like NBAs, they have like professional medical teams standing by all time. So anyone have any concussion symptoms, they're probably going to be treated as soon as possible. But even with that, sometimes accidents could happen. But imagine these are just after school play day. Later, 2 hours later, and then you were playing in the playground. The chances of just happens to have a medical school student walking by, it's pretty lame. So it would be really good to have some form of easy to access and also with relatively good accuracy tools to just diagnose you in the field and give you like an understanding of how well your how severe this brain concussion is, basically. So, not surprisingly, just like what the doctors would do inside of the field, but instead of using like a pen type of LED probe and then use the judgment by the doctor, we basically switch it to the LEDs on the phone and then let the phone or like the computer to do the judgment for you. Depends on different density of the light and different shining frequencies. It records the basically the retina changes inside of your eye under these stimulate, and then use that we predict a like how bad the concussion is, basically. There are also ways of using this for like eye prescriptions, or you can call them like optometry. So basically, you instead of using like those big setups in the clinic, we can also have like a standardized measuring add-ons to your phone, and then you look into the phone and then do the measurement. This is, let me give you a quick video.
In its simplest form, the test can be carried out using a small plastic device clipped onto the front of a cell phone screen. The patient looks into a small lens and presses the phone's arrow keys until a set of parallel green and red lines just overlap. This is repeated 8 times, with the lines at different angles for each eye. The whole process takes less than 2 minutes, at which point software loaded onto the phone provides the prescription data.
Yeah, so this project was actually developed at MIT Media Lab. So you'll see this type of video is kind of old-fashioned, and then with someone looking at you and smile. So these are like more, I guess, serious disease type of monitoring, but we can also do something like more behavior analysis that sometimes have strong, well, not sometimes, usually have very strong coordinations with some of your like mental health or like how stressed you are, etc. So, for example, researchers have done like the like pressure-sensitive keyboard and then capacitive mouses to basically let you use like adding on top of the existing keyboard and mouses that kind of keep monitoring or recording your, I guess, how hard you press your keyboard and then how angry you are with your mouse. So using that to interpolate how much stresses you are under. And so these type of monitoring devices are usually aiming for like longitudinal studies. So it's not like just this one day. You're expected to be using it for like a period of time, like in weeks or even months, so that the whole data can have they can observe like a more longitudinal effect over you. There's also a lot of work done in like the sleep quality monitoring. Basically, this is actually pretty straightforward. I think nowadays a lot of, like, for example, iPhones and some of the Android phones already equip this by default. Basically, it checks your movement, oftentimes by either audios or like checking on your snoring, etc. And another very, very important factors is first how much you touch your phone or let it light up. That's a very good indicator of how well your sleep quality is, as well as the battery level. So just to check on how much time you have on your phone, because people don't read nowadays. And then if you're still awake at night, chances are you're using your phone. So phone is a very good indicator of how your sleep quality is nowadays, because it's close to you and you interact with all the time. There are also works around more obesity monitoring, or like the behavior. This is like also within like the behavioral monitoring side. So basically, it will track how many steps or what's the distance you walked every day, and analysis where you tend to stay or where you tend to go. If you tend to go to like McDonald's and eat French fries, versus if you always go to Sweetgreen and get some vegetables and kales. So yeah, it will do a lot of like interventions on top of that. If you guys own like a smartwatch nowadays, you will notice a lot of them now have some type of intervention. If you sit too long, it gives you like a little pop. Should stand up and walk around, etc. These are all, I think, based on these like earlier work of the monitoring before. And there's also this very cool DUI, so basically drunk user interface, which is, I actually quite like this project. It was done at like measuring your motor coordination and cognition using performance matrix and sensory data after you're drunk, or after a certain amount of alcohol is being consumed into you. We had, I didn't directly involved in this project. I helped with them on the data collection. It's quite interesting. You can just spend your research money on drinks, and then all the participants just taking shots one at a time. And then every shot, they will ask them to do like some type of drunk user interface in game, essentially. We ask them to do like, math, or we ask them to solve a puzzle, etc. So I don't remember if this work has got published in the end, because the result we found is a little bit controversial. I think after like one drink, you actually perform the best, and then after that, it starts to decay. We don't really know why. I think it could be because the tasks we designed are a little bit still well within everyone's capability, so that if you only take one drink, it kind of just really, you just let go of your self-protection or embarrassment detector of yours, so that you just tell whatever answer that was already there. And then that tends to usually be right. So we end up having to redesign the method for that. So, but you don't drink and drive. There are also studies around, this is also around the behavior monitoring, but instead of using the sensory data, it's more like self-reporting, qualitative measurement. This is done at Dartmouth, actually, on like a school level, that to access the students' life quality by asking them to record in the app, the bedtime, wake up time, and number of conversations they have, positive effects, eating habits, all those things, just as a qualitative feedback inside of the app. So with all those data collected from the app, and then they do a bunch of as you were expected, processing via ML, and then to give some output on the, say, mental health or like the behavior term trends of those outputs from the right side. So give you some quick results here. So this is, I think, the Oh, sorry. This is basically the interpolated stress level. So if you on the okay, can you see my cursor? So this is the stress level, and each line basically corresponding to like an event that happens across the entire semester. And you will see that the gym activity dropped dramatically during the midterm and kind of never come back until the end of the semester. For the stress level for like that line, it peaks at roughly the midterm a little bit after. I guess people realize that, holy cow, I did not do well, and then I might fail. And then later on to the final, I guess the ship is already sailed, so not much you can do. Also, this is like the conversation duration they collected during the semester. So at the beginning, as you imagine, everyone was pretty chatty, and then after the midterms, the conversation frequency kind of at the low point, which obviously reflects on this class, because right after midterm, this is like the lowest attendance rate that we ever seen in this class. So I guess the study does show something that's very common across different student groups. And then later on, things goes up and then peaks at final, because I guess you need to study with peers to get a good grade. So quick question for you guys. So what's your feelings about doing these surveys with sensory data rather than like questionnaires? Do you have any concerns, or do you think any pros or cons within these two type of approaches? Talk to your neighbor for like 30 seconds and then. All right, guys. So I guess first, is there any benefits using sensory data over questionnaire or like self-reported data? Anyone? Yeah.
I mean, it's probably going to be more convenient because it's like more an automatic process. It's like
Yes.
time on your day.
Mm-hmm.
And I guess it could also possibly eliminate some bias we were kind of talking about. Like if you're just filling out a survey, it might be like not
Yes.
accurate always.
Exactly. That's a very good point. So first, it's almost like automated. It's like unobtrusive to your daily life, which is a plus. And the second is it's much, I guess, real to what you actually do. I think there is the famous theory, a report on like how Netflix became so successful in the end, and compared to other competitors at the time. Other competitors at the time usually uses what people report was the best movie they like. Obviously everyone's going to put, I don't know, Beautiful Mind or like Godfather, etc. But how many people actually sit down and watch those movies? In the end, you probably like most people would like, I don't know, Hangovers or those type of movies better, but they just never say it because whatever you put into the questionnaires or those self-reported forms, oftentimes it's a reflection of how you think yourself is or how you wish yourself is, rather than who you really are. Sometimes they can be the same person, that would be great. But oftentimes for the average people, there's some gaps in between. But a little bit on top of that. So but nowadays with more studies on the psychology side, researchers are learning to integrate these type of potential biases inside of their surveys or self-report questionnaires, so that we can hopefully get rid of these biases, self-biases, as much as possible. So what are the concerns of using sensory data rather than using like self-report? Yes?
The sensors are just like, you have a microphone and camera, everything turned on at all times.
Mm-hmm.
That could be a privacy concern. I wouldn't want my phone listening to everything I do at all times.
Exactly. That's a very good point. So the privacy and sometimes even like security concerns of how your data is going to be interpreted. Like you mentioned, you don't want your phone to listen at all time, but chances are it is right now. So, not much we can do about it. But still, it's good to limit all those type of additional sensory data that are related to your daily life that's being given to the peoples that you don't know or don't trust. Not that researchers are untrustworthy, but you never know how those data are stored. It can be like some data linkage or some other data security issues happening. So next, we're going to move on to like wearables. This will include, for example, the smartwatches or generally the stuff or devices that go onto your body. Why are we doing a lot of, or like when we can, we're doing things on wearables? Because for measuring the signals of the body, the closer the device to the body is usually the better. It's basically closer to the source, and then usually give you a better or less filtered data, basically. And let me give you some examples here. First example here, they have these wearable things around your neck to essentially measuring your throat. And it's mostly sound-based, so basically by monitoring the sound that happens across or around your neck area, it will be able to identify things like eating or coughing or laughing, breathing, etc. So it's able to do like some event classifications based on those audio inputs. So these things obviously can be used for example, some of the behavior monitoring, like diabetes, how much time you spend every day to eat compared to like an average person, or for like the stress or mental, like how much time you spend laughing every day versus if you don't laugh at all during your day. So these are all the things that these type of wearable devices are capable of monitoring. And we also have these more like, for example, for correcting or for help assisting the color blindness. So the color blindness, people unfortunately will be seeing something as colorful as left to something more like on the right. And then it's pretty decent amount of the population, so 8% of the overall males and 0.5% of females were suffering from this disease. So yeah, sucks to be us. And we have like different categories of different color blindness. So it's kind of hard to have like one device that just fits everyone, right? So one of the earlier studies around this is back in the day, I'm not sure if you guys still remember the Google Glass. That was like super cool when it came out. Everyone thinks, oh my God, this is going to change the world. And then, I actually interned at the Google AR team a couple of years ago, and then they were building this next generation AR platforms, pretty much similar to Apple's Vision Pro. It's going to be released soon. They in collaborate with Samsung. These are all open information, so it's totally okay for me to discard. I think they're pretty much going to release it this summer, I think, somewhere there. And then I remember during the entire like Google meeting, that meeting is all about the AR team. And the first question that popped up to the CEO, to the PCHI is, how do we prevent it from failure again from Google Glass? And the immediate response, I think all those executive folks have been well trained. First, we never had a failure for Google Glass. We pivoted to more business users and all that. So, but anyway, it was a great product at the time, very cool technology. Just I think in the end, the battery didn't really catch up. But at the time, a lot of the accessibility work was built around these glass form factors. For example, the color blindness, essentially it captured the picture and then do the color analysis, and based on your color blindness category, and that changes that into a color that's more recognizable to you, and then present that to you. I know also a lot of work for these are done for like the voice or like the audio. For example, like translations, etc. Those are also some work has been done through these wearable glass form factors. Also, we also have like wearable devices for like muscle engagement. This is one of my previous work, utilizing the electrical impedance tomography, and it was used. This technique is usually used for like lung function monitoring and also like cancer detection in clinic. We use it to reconstruct essentially the internal conductivity of the body part and look at what's the volume changes of the muscle, and also how much blood was inside, fused inside or get out of the muscle area. Use that to interpolate a muscle engagement level around the surrounding area. So, okay, I did not expect this. But basically, we built this in like an AR environment. Also, later on, we built this to have like in collaboration with Mass General Hospital and Harvard Medical School to deploy the devices for like patients with implants in them, and then use that for the unsupervised rehabilitation, post-surgery rehabilitation. So yeah, you don't have to wear all those suits. These are just for the user study case. We were trying to have like a study to evaluate how accurate or like how trustworthy our data is. That's why all the participants in the study were wearing this type of motion capturing suit. I'm sure if you guys are familiar with this, this is basically what they use in the movies when they're trying to build a lot of cool anime movement. Another thing that's commonly can be monitored through the wearable devices is also like stress. So basically, this have very strong causes to like sociological and psychological damages, and then it damages or like it affects your real-time performances and reduce your productivity, as the previous research shows. Also, in the long run, you have like direct affiliation with like cancers or heart diseases if you suffer from high pressure for a long amount of time. So there are different type of signals to look for these. For example, we have the EDA signal. Have like a very strong coordination with the stress level. It's called electrodermal activity. Basically, it measures the skin conductance, which if you sweat a lot, then that signal changes. So it essentially uses those signals to interpolate how much stress you are at the moment, with a few other signals, of course, like for example your heartbeat, ECG signals, etc. One of the devices they build is this little flapping butterfly. So essentially, you put it on your finger or somewhere. Whenever it detects you become stressed, the whole little butterfly just flips and then give you like a heads up, hey, you're stressed. And it turns out it doesn't really help, because users are usually more stressed once you're made aware that you are stressed. It's kind of like tell you to go to sleep when you're like totally sober. So yeah, did not end up very well, but it still got published because it's new findings, right? If it works, great paper. If it doesn't work, if you find the great reason why it fails, then that's also a good work. Other approaches for like stress or like anxieties, we also have the like more interventing methods. So this is like a wearable smartwatch thing that have a few of these moving dots on the back. So essentially, whenever it detects you are under stress, meaning your heart beats too fast, and then the EDA signal showing that you are sweating, it kind of gives you this little vibrating at a very certain rhythm. And then this method actually improved to able to help you be like stabilized at a more, I guess, healthy heartbeat, for example. This has been proved being quite, useful. So next, we will be moving on to the wireless sensing. Pretty cool. If you think about this, the wearables, we have it on body, and the smartphone we have, it's pretty much like the arm distance from your body, or but you're still like touching your device, right? The wireless is like the sensing modality is even further away from you, and it does not require any instrumentations on the body, on you. So essentially, it could be like an area sensing for a target area. As long as you are physically presented inside of this area, your signal is able to be captured or announced, which is pretty good if you think about it for like home measurement, for home monitoring, because chances are you're going to just be at some location in your home, or even in like the clinic waiting room, for example. We have some form of wireless devices, and then it's able to monitoring like a few patients in the room. That one is a little bit ongoing. Still a lot of efforts needs to go into that. But the home monitoring is along the way. But anyway, give you some like some cool works around this area, around like the wireless monitoring. We have researchers using essentially Wi-Fi signals to look at the reflection of the Wi-Fi signals, and then with that, they are able to extract out the chest expansion changes with the reflection. And then in that, they're able to reconstruct the breathe pattern as well as the heart rate from that. So let me give you a quick video on that.
This is our device. The device transmits a wireless signal which reflects off a person's body and comes back. It captures these reflections and analyzes them to infer the person's emotions. Specifically, our algorithms zoom in on the wireless reflections to extract the minute variations due to breathing and heartbeats. We then further analyze these reflections to extract the breathing signal and the heartbeat signal. We then zoom in more on these signals to obtain individual heartbeats and breathing cycles, and feed these as features into a machine learning algorithm to recognize a person's emotions.
I love the days when they're still using pasta machines to represent ML. Nowadays, it's all just blocks connecting all
Our
together.
device can recognize emotions with an accuracy of 87% while relying purely on wireless signals.
Yes, so this work was done at MIT by Professor Dina Katabi. She was on my, never mind. So the student who did this work, the Asian guy you see in the video, he's now a faculty member at University of Pennsylvania. And they later on move on to using the similar technology, but use it for like a sleep stage monitoring. So and also the sleep posture monitoring.
Today, monitoring sleep is done in the hospital with many sensors. It requires the person to wear them all over their body and spend the night like that, making it hard to actually sleep. In contrast,
This is called sleep
new
study.
MIT
Yeah.
technology monitors your sleep without any on-body sensors. The person can sleep comfortably at home, while the device sits in the background and transmits a low-power radio signal to predict the sleep stage. So how does it work? It uses an advanced AI algorithm which takes the radio signal as input and feeds it into a new deep neural network and outputs sleep stages. Its accuracy is comparable to the accuracy of a sleep technician, which is about 8.
Yeah. Sorry for the little bit cheesy video. We don't usually do that. The reason this video looks like this is because they end up doing a startup around this. So this video is actually meant for showing their technology to VCs and stuff and get everyone excited. Anyway, along the sleep monitoring line, there's also ways using what they call like the Doppler effect to detect your sleep interruptions. This is basically there's a module that transmits like a single tone to you, and then basically based on the reflected reflect the signal, we're able to decide whether you like kind of like moving during your sleep or like move a lot, etc. So you can think of them as like a posture detection and use that to decide like which sleep stage you are at the moment. And yeah, I think you should probably all familiar with Doppler effect. Basically, sound, if you're going towards it, it changes the pitches. If you go further away from it, it changes the pitches. So a little bit on like the near future end, we also have the on-body health sensing around. So for example, there have been like a lot of efforts working to get these flexible electronics that's working like a tattoo that directly attached to your skin that can either just directly measure your biosignals like like electrodermal, like the EDA signal, or your like the heart rate, or some of the electrochemical signals, etc. One of the, you can also like attach some of the active components on it, for example, attaching like an additional light source. So this is essentially a PPG sensor that give you like pulse information. Little bit more advanced, we have the electrochemical detections with, basically they look at either your like blood flows by different temperatures with different areas, or it looks at some of the, or it look at some of the biomarkers on your body. Basically, when certain things happened, your body on the body surface might, in your sweat, for example, might have certain type of proteins being generated correlates to different type of conditions of your body, and they have a lot of work nowadays to have these type of sensors that essentially like a tattoo attached onto you and doing those biomarker analysis. A lot of these work, I think probably like one of the most front end of this route is at Professor Joseph Wang at University of San Diego. And a lot of his students and the grandchildren in terms of the academia hierarchy trees are at different universities now. We actually just interviewed one of his grandchildren in terms of academic tree to our department. So if he ends up going here, and if we end up making him an offer, this could be some really cool work if you guys are interested for your summer research, for example. And we also have like the future, basically. It's a little bit, obviously, it's usually around like the implant and some other mechanism. Of course, right now, like inside of the clinic, these things are like pretty widely deployed. If you have, a lot of people have like some type of like devices within their or near their heart to help you like regulate your heartbeat, for example. But in like the more like outside of the clinic or easy to implant route, it's still like a very active research field to how to get these biocompatible sensors be implanted into you with like minimal amount of invasiveness and then still get decent result out. There's also like other, I thought I have like one more slide here, but basically a lot of work around like bioprinting. So you guys are familiar with 3D printing from like MATLAB stuff, right? But imagine instead of using those filaments, plastic, etc., but using the cells and gelatins and collagens all together to print out like a functional tissue or even functional organ. That's a very active field, but not quite reached EECS yet, because the biologists and the doctors, well, usually the biologists, they're still trying to figure out how that happens from like a physical perspective. So once they figure out, we're able to jump in and then help with some hardware design and obviously magic ML models and then do some cool stuff together. So generally speaking, what are the challenges of these health sensing in embedded systems, right? There are a few of them. Let me just identify them. Because we're trying to make it like, so in general, we're trying to make it like easier to access, basically corresponding to like portability and oftentimes low cost, which very much align with where the whole embedded system is going for. So quite relevant, and also make it easy to use. because chances are these devices are going to be deployed within the users or like patients, so to speak, rather than being operated by the doctors or clinicians who have a lot of professional domain knowledge. So this how to deploy these devices when to achieve still comparable results with in-lab test is actually a quite challenging task. Another big one, I will probably argue this is almost like the top one challenge is the ground truth is usually hard to get. There has been a time where all the ground truths are very easy to get, the heartbeat, the aspiration rate, etc. But all those signals have been heavily studied, and nobody can think of any new things around that. So the remaining part are the signals or the symptoms that have much harder ground truths, very hard to get the ground truths. This is partially because, everyone is very different, and even within the same person, your conditions can vary based on a daily basis. Even, for example, the food intake or like your mood can sometimes affect a lot of these biosignals. So ground truth is pretty hard to get. And also make things even worse, not everything is like directly measurable with sensory approaches. For example, some of the chronic pains nowadays, most of the measurement I'm aware of are still like indirect measurement. It measures, how much sweat or what's heartbeat, etc., to give you like a estimate of, that person probably is experiencing some pains, but there's not really a good ground truth or gold standard, as we call it, for those chronic pain measurement, as well as like mental health. Like, nobody knows. So. Cool. So as like a quick summary, so we have the novel health sensing technologies that work at various distance at your body to help with measuring the biomedical data or just in general health-related data at hopefully anywhere and all the time, as well as provide more data points and accessibility apart from just the clinic. There are also other more areas in health, for example, or like around this area. So little embedded system devices that help you build your own thing. For example, we have this microfluidic toolkit. I think I'm not exactly sure if this is still purchasable, but basically it helps you to work with some like probing data in suite, basically help you or guide you to mix those medicine on the fly. Let me show you a quick video on this. So, so basically, you can there's like a little probe you can put in the intake medicines, and then this whole device helps to move them and then mix them in like a certain order. You can have multiple of them. So, not sure if you guys are familiar with the term biochip. So, biochip is basically kind of like a computer chip, but like a mechanically lot of tubes underneath connected that by detecting which probe you first trigger, that determines which type of fluid mixing with which type first. So this is essentially like a embedded system version of the biochip. Yeah, I think these are still probably still available for purchase. Not sure. And we also have these little device things they built at MIT IDC in the International Design Center. Basically, it's for similar to before, like the little biochip. It's for like easier, like the medicine mixing or like affordable health, etc. Rapid diagnosis, etc. So, yeah. With that, this is the end of the special topic. If you guys have any questions or interest, feel free to come to my office hour or after classes. We can have a nice chat of anything around this round. So thank you for coming, and I will see you guys next week.
Hi.